Alright, so let's move to the Quartus Prime software. So we will open Quartus Prime and we are going to use this version. Okay, so let me move here. So this is our Quartus Prime starting window. So first I will select this new project wizard. Now click on next. Now this is asking that where you wanted to save your project. So let's browse the folder location. Now suppose I wanted to save this inside this Quartus 2 projects. For example, you can select any folder. Now create a new folder and give it some name. For example, the folder name is UART module. That is our project name. Now I will copy this because I can use this later. Now select this folder and now it is asking for the project name. Now remember that your top level module will be your project name and that is mandate. You cannot use two different names for your top level module and this project name. And if you remember that our top level module is UART module here. Okay, so I will use the same name as we have used for designing our top module. Okay, now click on next. So this will be an empty project. So click on this option and then click on next. Now here you can add multiple VHDL files for your project. Like we have used Notepad++ to write our VHDL programs. Then we have used Model Sim Simulator to simulate them. And now we are going to use the same VHDL files in this project. So here I can import all these VHDL files in this project. Okay, so for this I will click on these three dots and I will select the folder location where all the VHDL files are stored. Okay, so what I will do that I will copy those files from the model sim UART project. So that was our UART project. So here we have this source folder and you can see that all the modules are listed here. So I will copy these and I will go to my folder that is Quartus 2 project and that is our UART module project. So I will paste all these files here. And now I will select all these files and I can click on open. You can also copy this file from the Windows Explorer as well. Or even you can directly import these files from your Model Sim project as well. So all the steps will work fine. Okay. Now what I will do that even though I will create a new folder that is our source folder and I will move all these VHDL modules in the source folder. Okay. Now I can select all of them and then click on open. So you can see that all the files, all the VHDL files are listed here. Okay, now click on next. So now this is the page where you can select your FPGA device. Okay, so for example, I'm selecting this Cyclone 4E device. Now you have multiple filters here. So you can select the package. For example, I'm using this QFP package and the suppose pin count is 144. So select this. You have to select what FPGA you have. Okay. And now you can select this speed grade. For example, this is 8 in my case, and you can select whatever FPGA you are using. Okay. So for example, I'm using this for this project. So I will select this FPGA device and then I will click next. Now here you can select your simulator if you wanted to use it. Now because I'm not using it because I have already simulated my project in Model Sim. So I'm not going to select anything from here. So I will leave it as it is and simply I will click on next and then click on finish. So first thing what I will do that I wanted to use the recent compiler for our VHDL project. Okay, so what I will do that I will select this FPGA device that I have selected. Now right click and then click on settings. Now you will see this type of window, and here you need to go this compiler setting and then VHDL input, and you should select this VHDL 2008 version. Okay, now click on apply and then OK. So you can see that we have this module, UART module, as a top level module and as our project. So first thing that I will do that is analysis and synthesis. So you can see that multiple buttons here, so you can use them. So this is the button here for analysis and elaboration. So click on it. So now you can see that process has been started. You can also see the status here at the bottom. Okay, so now this is completed. So this analysis and elaboration that is marked with the green color, and that is completed in 8 seconds. Now once you do that, you can see the hierarchy of your top level module. So that is our UART module, which is our top module, and here we have two modules. So that is transmitter module and that is receiver module for UART. Now, if you expand them, you can see that all other modules that has been used. So for this RX module, we have used this baud clock generator. We have used shift register and sync component. Same for transmitter module, we have used these two elements. Okay, so that is the hierarchy, and you can select the hierarchy from here. So if this view is not coming for you, so you can select the hierarchy from here. Else you can select the files. So all the VHDL files are listed here. Okay. And now because our Quartus Prime software has completed this analysis part, this means that all of our VHDL programs are free from any syntax error. So now what I will do that I will assign the input output pins or input output ports of our top module, and we will map them with the FPGA board pins or FPGA device pins. Okay, and for that we will use pin planner. So if you look at this multiple buttons here, there you will see a pin planner. Okay, so I will open it from here. So you will see this particular view. So this is your FPGA device, and that is the device that you have selected. So we have selected this from the Cyclone 4 family, and this FPGA was having 144 pins. So you can see all the pins listed here along the four sides of this FPGA. So this is side A, this is B, this is C, and this is D. And our Quartus Prime software also captured all the input output signals or all the input output ports from our top module. So if you look at this table, so we have this clock, reset and receiver as an input pin. Okay, so you can see that Quartus Prime already detected the direction of your input output ports. Okay, so these three are the inputs and this transmitter pin is your output. Okay, so what I have to do that I have to map the physical pin of this FPGA to these ports of our top module. Okay, so for example, we have this clock signal or clock port, and we can use these pins for this clock signal as an input. Okay, now the question is that to which pin this clock port has to be connected, and that need to be specified from your datasheet that you will be received from your FPGA board manufacturer. Okay, so if you are using the same board that I have, then you can map these ports to the same pins that I am mapping. But if you are using a board that is manufactured by someone else, then you have to follow that particular datasheet. Okay, so for example, in my case, this pin clock is connected to pin number 23. So what I will do, simply I will write pin underscore then your pin name. For example, I wanted to connect this pin with pin number 23. So once I do this, you can see that this pin 23 is highlighted, and now this is reserved for this clock port. Okay, similarly we have this reset input. Okay, so I will write pin number 25 for example. So this particular pin is assigned to the reset of our top module. Okay, similarly I will repeat the steps for our receiver pin, that is for UART, and same for UART transmitter pin. Okay, So receiver pin is suppose pin number 115. So that will be pin underscore 115. And suppose this transmitter pin is connected to pin number 114. Okay. Now if you notice, then when I have updated the location of these ports, our Quartus Prime software already detected the IO banks respected to these FPGA pins. Okay. And this is because these 144 pins of this FPGA must belong to some specific bank. And these banks can be in different numbers for different FPGA devices. So for example, this particular FPGA device have 8 banks, and you can select individual power supply for each individual banks. Okay, so you can take is like this particular FPGA device are divided into 8 blocks like this. Okay, so there are 8 blocks and there are few pins, and each and individual pin of this FPGA must be belongs to one specific bank. Okay, and these are pretty standards for the FPGA devices. So that's why Quartus Prime able to detect input output bank from the pin locations of your FPGA. Okay, and now we have this input output standard. So by default they are selected as 2.4 volt. Means all of the banks are expected to get the VCC voltage of 2.5 volt for each individual bank. Okay, but if your board manufacturer is using a different power supply or different voltage for different banks, then you have to map it. Okay, so for example, if your FPGA board manufacturer is using 3.3 volt, then you have to select this 3.3 volt. Okay, and maximum manufacturers are using this 3.3 volt standards, so you have to select whatever your board manufacturer is using. Okay, so let's give these settings, and now we have this current strength. Okay, so basically it is telling that how much level of current that pen should flow. Okay, and because we are using a low speed device at the moment, because this is a UART and we are only having the baud rate of 115520, so this is a slow speed device. So for this project, even you can reduce the current strength. Okay, for example, I can use a 4 milliampere. Okay, let's do the same. And now that's complete our pin planning. So these two columns are identified by the Quartus Prime, and that is port name and their direction. So we have this FPGA view here. This is our selected FPGA, and here we can see that all the pins are listed here. And then we have assigned the FPGA pin sequence with the top level module or the ports of our top level module. Okay, and accordingly, once we define the location of these ports, input output banks from the FPGA is already defined by the Quartus Prime software. Okay, same the V reference group. And then we have defined the input output standards as per the FPGA board manufacturers, and we have also defined the current strength based on our project needs, right? So that's complete our pin planner. Now you do not need to save all of these things in Quartus Prime software, because once you change anything here, then these settings are automatically saved. Okay, so you can just close this window. And now what I will do that I will give a full compilation to this top level module. So if you go here, then you will see this start compilation button. Now I will click on it. So it can take little time. So you can see that the progress is ongoing, and same you can see this the status bar here at the bottom section, and here you can see the timings. So now you can see that everything is good, all in the green section. And let me quickly brief what are these things. So analysis and synthesis. So here it will compile your programs or all of your VHDL modules, and then it will convert it into the RTL matrix. Okay, so that's the job of analysis and synthesis. And next is filter or place and route. So whatever the structure that has been generated in the previous step, now Quartus Prime software will place these elements inside the FPGA and also define the route of signals. Means all the interconnections between those elements will be defined by this route. Okay, so that is place and route. Next section is assembler. So here Quartus Prime will generate a programmer file that can be used to program your FPGA device. And the last section is timing analysis. And this section will tell you if your module is violating any timing constraint. Now coming to this main section. So this is our compilation report, and this is actually very important. So first it is showing that what version you are using, what is your top level entity, what FPGA device you are using and belongs to which family. Now total logical elements. So you can see that this FPGA that we have selected, that have 6272 elements inside it. And out of these, we are using 70 elements in this UART project. So this is actually a very small project, okay, which is only consuming only 1% resource of your FPGA, right? Now you can see that you are using 57 registers, and next is total pins. So you know that you are using 4 pins out of these 92 pins available in the FPGA. Okay, so that contributes around 4% only. So these 4 pins are clock, reset, receiving pin and transmitting pin, right? So that's the wholesale summary. But if you look at this tab, you can see that everything is good except this timing analyzer. So you can see that this is in red, means something is not good here. So if you expand this, then you will see there are a few things that are in red. So this is in red, this is in red, this is in red, this is in red. So we need to look at what are the timing problems and how we can solve them. Okay. So if I click any of these red highlighted area, then I can come to know that what is the problem. So for example, for this, I can say this setup summary. And you can see that this clock is having the negative value. These are expected to have a positive value. And because these are negative, so that's why it is in red. Now let me quickly tell you that by default, Quartus Prime software is considering that you are going to use 1 gigahertz of frequency. But for our project, we are expecting to use a 50 megahertz of clock frequency, right? And there is a huge gap. And 1 gigahertz of frequency is really a very high frequency. And if you are using a 1 gigahertz of frequency, then the variation is just 2 nanoseconds. And for this endpoint TNS, that is 76 nanoseconds. So I'm pretty sure that for the 50 megahertz of clock frequency, there will not be any timing problems, right? So we can simply ignore this, but even there is a better way that I can tell this Quartus Prime software that I'm going to use a 50 megahertz of clock frequency, not 1 gigahertz. Then all of these warnings will be wiped off. Okay, so I will prefer to use that way. But before this, let me quickly brief what all are these things. So you can see that these are started from slow or fast. So what Quartus Prime is doing, that it is considering the fastest model and the slowest model for the FPGA, and then it calculates these values. And it is also telling that how these devices will behave at different temperature. So this 0C means at the 0 degree centigrade and at the highest temperature of 85 degree. Okay. And for this, we can see all of these elements are in red mark. So for this, what I will do, I will tell the Quartus Prime that I'm going to use 50 megahertz of clock frequency. Okay. So first I will click on this button. That is our Quartus Prime timing analyzer. And here you will see this update timing netlist. Okay, so just double click on it so that it can run. And you can see that is in green. So that's done. Now let's minimize this window. So at first I will create a new file. So I will go to this file and I will click on this new. And this time I'm going to create a constraint file. So I have to select this synopsis design constraint file. So this is SDC file. Okay, that is synopsis design constraint file. So that will be present inside this other files. Okay, so I will select this. Now click on OK. And now this is the time to define the clock frequency. So for this, what I will do, that I will go to this edit section, and here you will see the option of this insert constraint, and the first option is create clock. Okay, so I will click on it. And this type of window you will see. Now first I have to give some clock name. So give it, that is 50 gigahertz. You can give any name. and it can be different from your top level module port. Okay. Now this is a 50 megahertz and now it is asking for the period. So for this 50 megahertz of clock frequency, the clock period will be 20 nanosecond. So you can see that it is in 20 nanosecond. So for 10 nanosecond that is high and for another 10 nanosecond that is low. Okay. Now, because if you wanted to use a 50% duty cycle of a clock frequency, so you can leave these two fields blank. But if you wanted to change the duty cycle of your clock, then you can tell that when it will have the rising edge and when it will have the falling edge. Okay. Now I have to select the target. So for this, I will click on these three dots and it will show up with this type of window. So from here, I will select this get ports and I will click on this list button. So it will list all the ports from your top module. And now I have to map the port which belongs to this clock 50 megahertz. Okay. So this clock signal will be belongs to this 50 megahertz of clock, right? So I will select this and I will move to this selected window. Okay. So this is selected. Now click on OK. So this is the statement that will tell that you are going to use a 50 megahertz of clock frequency and that will be mapped to the clock port of your top module. Okay. Now click on insert. Now click on enter, save this. And now I will save this with some relevant name. For example, this is a timing constraint. So I will save this as the same name so that I can remember what's inside this file. Once you save this, then I will recompile my program. Okay, so I will click in this start compilation button and then it will start everything. So you can see the progress here. So wait for a while so that it can complete. And once it's done, the new report will be generated here. Okay, so you can see that still this timing analyzer is in the red section. Okay, so now I will expand this and now you will see that these elements which was in the red mark, now they are green or they are good. Okay, means there is no timing violation on the clock signal anymore. Okay, so you can see the setup summary now. So everything is good. There is no red. So everything you can check and even you can go through all of these elements here listed here. But I'm just telling you the important ones so that this video won't be very long. But if you see, if you go down and you see, then we still have this red mark section that is inside this unconstrained parts. And if I click on summary, then it is telling that we have two input ports and these are unconstrained. Same, we have one output port that is unconstrained. And that is because these inputs that we are having inside this module, that is our UART module, and all of these three inputs are asynchronous in nature. Means they can reach at the input port of the FPGA at any point of time. And we have synchronized it with the clock internally wherever they are needed, right? So we do not need to worry about the timing constraint of these inputs or even outputs, because output can reach also at any point of time, which we have defined inside our modules because we have write the VHDL code for them, right? So what we will do that we will tell the Quartus Prime that simply ignore these constraints. Okay, so for that what I will do that I will go to this timing constraint and again I will go to this edit tab and I will select this insert constraints and now I will select this set false path this time. Okay, so once I will select this, I will see this window and that is showing from and to. Now because let's define them for the inputs, so I will select this from tab. Okay, so for this I will click on this three dots. Now I will select the ports from here and then I will click on list. Now it is giving me error that timing net list does not exist because that is updated and we have not selected it again. So for this what I will do that I will cancel everything and I will open the timing constraints once more time. So this is our timing analyzer, but remember I have not closed this window. So this is already opened in the side here. So if you see that this is not ready at the moment because these are marked as black color. So what I will do, I will simply double click here and you can see now this is done. Now I will minimize this window and follow the same steps again. Okay, so go to edit, now insert constraint. Now click on this set false path. Now click on from, because we are now doing this for the input ports. So we will click on these three dots. Now select the ports. So get ports. Now list them. So now you can see that everything is listed here. So we have 4 ports, and from these 4 ports we have 2 as an input, because for clock we have already defined the constraint. Okay, so we have this receiver pin as an input and this reset pin as an input. So I will move them to the selected area, and now click on OK, and now select this insert. Okay, so these are inserted. Now save this, and now we will repeat the same step for the output port. Okay, so again I will go to this edit tab. Now click on this insert constraint. Now select this false path. Now because this is the output, so I will select 2 this time. Okay, now click here on these 3 dots. Now select the ports, so it will get the ports. Now click on list. Now this time this is coming because I have not compiled my program yet. Okay, I will do it single time after doing this. Okay, now I have to select the output port, and we have this output port. Okay, this is the only output we have. So I will select this and I will move to this selected area. Now click on OK, and now click on insert. So these 3 lines are inserted. One for the clock signal or clock input, these two for the 2 input ports, and the last one is for the output. Okay, now save this, and now we will compile our program one more time. Okay, so click on this button. Now the compilation is started, and you can see the progress here. So it can take little time. So we will wait for it to complete, and you can see that's about to complete, and that's completed 100%. Okay, now if you focus here, then there is no violation about timing. So now this is not in red. Okay, so that's good. So what we have did, we have compiled our program for any syntax error, and we have developed the synthesis from here. Then we have given the pin planning, where we have specified all the ports and map that with the FPGA pins, and then accordingly Quartus have generated the place and route files and performed this action, and once it's done, it has generated the programmer files for us. And we can also see multiple files for different type of reports that you can analyze based on your needs. Okay, and I have showed you whatever is in red, and I've also told you that how to fix them. Okay, now if you wanted to implement this program into the FPGA board, then simply you need to open programmer. So if you move to this buttons here, you will see the programmer. Okay, so simply open this, and this is your programmer module or programmer window. So let's quickly see what it is here. So this is your top level module. So that is your UART module.sof. So that SOF is your programmer file that you can use to program your FPGA device. Okay, this is the device name that you have selected. This is the checksum, kind of a verification done by the Quartus Prime software. This is a user code, you can ignore this. And we have this program or configure button, so that is ticked. Okay, now this time I have not connected with any hardware or any FPGA device. So that is why it is showing me no hardware. But if you connect your FPGA device with the J tag, then your device will be listed here. Okay, if not, then you can click on this hardware setup, and that hardware must be listed here in this box. Okay, you can just simply select it and then click on close. And once you do this, and once you select this programmer file, you will see that this start button will be highlighted. So once it's highlighted, you just simply click on this start button, and then you will see the progress here. And once it's 100% complete, then your top level module will be implemented into your FPGA device. Okay, so that's how you can program your FPGA device and load this SOF programming file into the FPGA device. Okay, now let me quickly show you the folder that has been generated by this Quartus Prime software. Okay, so I will open the file explorer, and here you can see that we have developed our program for this UART module inside this Quartus 2 projects folder, and here we can see this UART module. So that UART module is our Quartus project, so that is QPF in format. And we have this source folder that we have generated or that we have created to copy all our VHDL modules or all of our VHDL files So you can see that all the VHDL files are listed here. And if you see, then there is one more folder that is generated by Quartus Prime. Okay, if you open it, then you can see there are multiple files are generated. So I have already told you about this SO file. So that is your programmer file, and you can use this file to program your FPGA device. And you can see a couple of more files here that you can do it in the notepad. But the one file that I wanted to show you, that is QSF file. Okay, so that is your Quartus setting file. And whatever the settings you have used in your project, that all the settings are listed here. So if you open this into the notepad, so open with in the notepad, then you will see all the settings are listed here. Okay, for example, what device family you have selected, what FPGA device you have selected, what is your top level entity, what Quartus software version you are using, date and time when it is created. Also, all the VHDL modules are listed here that you have used. So you can read this one by one, but important thing is this pin section. So you can see that whatever the pins we have defined for our top module, so these are also listed here. So you can use them and you can change them as per your need as well. Also, you can see that we have changed the voltage level or the input output standards from default to 3.3 volt. Okay, so you can see that we have changed this for all these 4 ports. Okay, same, we have changed the current strength to 4 milliampere so that you can see. So whatever the changes except the default things you have made into your Quartus Prime software, so all of these settings are recorded here. Okay, so you can use this file as a reference. Okay, so that's it for today. That was our complete UART project where we have designed a UART transmitter, we have designed a UART receiver, and then we have designed a UART module that was echoing back the received data, and the data that has been received at the receiving port that has been transmitted back through the transmitter module. Okay, so I think that is a good practice project, and hopefully you have learned something from this complete project of this UART module.